Okay, welcome to this special lecture recording for ECE 3337, Signals and Systems Analysis. So this recording is intended to help you understand these operational amplifiers or op-amps and how to analyze circuits that include op-amps. Okay, the reference material for this is still Chapter 4, Sections 4.5 and 4.6 of the ULB textbook. Okay, and op-amps or operational amplifiers are the most versatile and useful electronic device or component ever invented. I used to use them as a student when I was your age, and they're still out there. They're still as useful as ever, and I think they'll continue to be useful essentially forever, as long as there's electronics. Okay, now what we want to do is to figure out how to analyze circuits that include these op-amps. Okay, now this is not a course on electronics, so our discussion here will be quite a bit less detailed compared to what you would learn in the electronics class. Okay, we're mostly focused on using ideal op-amps and on applying ideal op-amps, applying the Laplace Transform based methods to circuits that have ideal op-amps. Okay, in other words, we're just going to talk about op-amps to just the level that's necessary to get through ECE 3337. Okay, so let's start off with the basic concept of an amplifier, right? As the name sort of suggests, an amplifier is a device or something that can amplify a signal. In other words, it can strengthen the signal, right? So if you have an input voltage V in, it has an output voltage V out, that's some number A times V input voltage, and we sort of expect this number A to be more than 1. Okay, so this number A is what we call the amplification or the amplification factor. Okay, and more commonly, okay, we call it the gain. So the gain of the amplifier is sort of the number by which it multiplies the input. Okay, now from a circuit perspective, the amplifier looks like this. So if all voltages are specified relative to a ground signal, right, then the input signal, V input, sort of looks like an open circuit, right? In other words, there is no current going in, right? So in other words, the amplifier simply senses the voltage at the input, okay? And if you peeked in like this would look like an open circuit. Okay, in other words, the input resistance, okay, is infinity, right? And on the output side, okay, it simply looks like a voltage controlled voltage source, right? In other words, this is a voltage source whose value is A times V in. Okay, and this is the output voltage. So on this side, it can put out just about any current that you wanted it to. Okay, now in the real world, the op-amp can probably not have infinite input resistance, but chances are it'll be a very big number, right? It'll be pretty decent. And on the output side, it cannot put out any arbitrary current, but it'll be some decent number. So every op-amp will have some operating conditions within which it satisfies this relationship. So what I'll do is I'll assume that we are operating within the capabilities of the device that we are working with. Okay, so let's go on to the next version of the amplifier. So suppose you had an amplifier with two inputs. Okay, so I'll call the one input a plus and the other one input a minus. Okay, and suppose we are given it two voltages, Vp and Vn. The output in this case is A times the difference between Vp and Vn. And for that reason, we call it a differential amplifier. It's taking the difference, okay, and then it's going to amplify that difference, right? So A is the same thing. It's called the amplification or the gain of this differential amplifier. Now, from a circuit perspective, this guy looks very much like this guy, except it's got two inputs, okay? So you got VP, we got VN, okay? They both look like open circuits, okay? Because there's no current going in, okay? There's no current going into this, okay? And so the input impedance here, okay, is infinity. And on the output side, it's a controlled source, okay, and the output voltage is A times Vp minus Vn, okay. So now in the real world, one of the things that's going to happen is that we cannot get infinite voltages, okay. So what's going to happen is that an op amp is going to be supplied with a voltage source. Typically we have two voltage sources, a positive voltage source, okay, we call it plus VDC, and a negative voltage source, minus VDC, okay. And of course we got the two inputs, VP and VN, and then there is an implied ground in all of our circuits, okay. So the input is a differential one, okay, VP and VN, and the difference of these two voltages is amplified by some number A, okay, so the output is VP minus VN times A. Okay. Now, one of the things that we're going to find is that the output voltage cannot exceed plus VDC and cannot go below minus VDC, right? So basically it's clipped off at these two ends, okay. And we also say it's it's a case of saturation, okay. That's another phrase that we use to describe this. So basically, if we describe this in input-output terms, the input is delta V, where delta V is Vp minus Vn, okay, and the output, okay, is A times Vp minus Vn, okay. And so for a small difference, okay, it'll behave quite linearly like that, okay. So if the difference is positive, you'll get a positive output. If the difference is negative, you'll get a negative output. But at some point, as soon as it reaches plus VDC, it'll get clipped off like that, okay. And if it reaches minus VDC on this side, it'll just clipped off like that. So now the slope of this curve, okay, is equal to A. Okay, so the higher the slope, the more drastic this curve is. So if A becomes infinity, okay, this will look like a clear, nice step function like that. Okay. All right. So now I just talked a little bit about the number A being large. Okay. So basically, what's going to happen in this case is that even the tiniest voltage, okay, is going to be enough to drive it to one extreme or the other. So when A is very large, okay, the input-output relationship for this op amp will kind of look like that. If A is infinity, this will be like a perfect step function. In this kind of configuration, we call it a voltage comparator. And for the obvious reason, right? So the two voltages being compared are Vp and Vn, okay? And when one of them is larger than the other, okay, so if Vp is greater than Vn, then the output voltage, okay, is going to be plus VDC. And when Vp is less than Vn, okay, the output voltage is going to be minus VDC. Now, of course, if Vp is equal to Vn, the output is going to be 0, okay, as one would expect, right? But if the slope is high enough, right, so this is the slope, then even the tiniest difference between Vp and Vn is going to be picked up on, okay? So unless they're like exactly the same, okay, the output is going to be one or the other. Okay, so we call this a voltage comparator circuit. Now, an op-amp is a differential amplifier, which is really, really good. So basically, an op-amp has, a infinite input resistance. Okay, so it doesn't consume any current at all. Okay, so the currents going into an op-amp are essentially negligible to zero. Okay, this is zero, this is zero. Okay, this is VP, VN, and on the output side, it's got, okay, a very strong voltage source, so it can output any current you want. Okay, except the output voltage, is limited by these two limits, the limits imposed by the power supply. Okay, and importantly, the amplification factor for an op-amp is infinite. Okay, so when we talk about op-amps, for the most part, okay, we sort of noticed here that this is a very jumpy kind of device, right? Even the tiniest input difference will get amplified by a big number, right? So if A is infinity, this is going to be a perfect step function, right? So how do we tame this jumpy device, right? One way to do that is to have some kind of a connection between the output and the negative part of the input. Okay, we call this negative feedback. Okay, it's called negative because, obviously the feedback is being given to the negative input of the op-amp. Okay, of course it's called feedback because, the output is being fed back to the input like this, right? So what does negative feedback do? Intuitively, right, suppose the output voltage is some value V, right? If we try to increase even slightly to say V plus delta V, right, then what's going to happen is that this delta V is going to show up here, okay, and that's going to affect the new voltage, okay, by some value that will eventually drive this delta V to zero, right? Because even the slightest increase on this side is going to get amplified a lot, which means the output is going to go down, right? Now, if suppose the output voltage tries to go to V minus delta V, right, the same thing is going to happen, right? Then this negative differential voltage, okay, is going to get counteracted because it's going to get multiplied by A. And that's going to, negative times negative is positive, so that voltage is going to get boosted, right? So what's going to happen is that this negative feedback has the effect of counteracting any change in the output, right? Even the slightest change in the output will immediately get counteracted because of this negative feedback, right? And because of that, the output, this op-amp, will be in a very, very stable kind of a mode, right? So we say that when there is negative feedback, okay, the op-amp is in stable mode. Now let's kind of take a look at what the stable mode means and what it does, right? So for example, if we have, VP and VN and V out like that, right? We know that V output for this op-amp is A times VP minus VN, right? So now suppose that VP, okay, is like V input, and Vn, okay, is the same as V output because of the feedback, right? So let's plug it in into this formula and see what happens, right? So V output equals, right, A times Vp, which is V input, minus Vn, which is V output, right? I'm being a little bit lazy. I didn't write the whole word I just wrote VO instead of V output, okay? It's the same thing. So now if we solve for this V output, right? So VO times 1 plus A equals A times V input. So VO is A divided by 1 plus A times V input. This is pretty cool, right? So if A becomes a large number, then this ratio is going to be very close to 1. So V output is going to be exactly equal to the V input, right? In other words, the limit, so let's think this through a little bit further, right? So if I write it in like calculus type language, right? So the limit of as A tends to infinity of A over 1 plus A times V input, okay, is simply equal to V input, right? Because this limit essentially goes to 1. Now, let's also look at the same thing a little bit differently. So if V output is going to be some finite number, right? And it's going to be finite, it's going to be some reasonable number because of feedback. Right? So in that case, okay, we can ask what is, okay, Vp minus Vn, right? So since V output equals A times Vp minus Vn, then we can see that Vp minus Vn equals V output divided by A, right? So the limit of Vp minus Vn as A tends to infinity is going to be 0 because this is finite, this is infinite, so the limit is 0, right? Now this is a big deal, right? What it's telling us is that when an op amp is is in stable mode, then the two inputs, Vp and Vn, okay, are going to be about the same, right? So whenever an op amp is in stable mode, Vp and Vn are in fact negligibly different from each other. In other words, they're essentially identical, or Vp equals Vn, right? So, and this is the basic trick. So whenever we are analyzing op amp circuits, we're going to take advantage of the fact that Vp and Vn are driven to be the same thing, right? And of course, this only happens when there is negative feedback, okay? If there is no negative feedback, then, in other words, if there is no negative feedback, then this is not necessarily true, okay? So with this, what we see is that our circuit, okay, has an output that's equal to its input, right? So we call this a voltage follower, okay? You might ask, what's the point of simply following a voltage, right? What it's doing is that it's providing a strengthening of the signal. So suppose the input voltage is coming from a very weak source, right? Without perturbing that weak source, it'll provide you with an equal voltage at the other end that can drive a much heavier load, right? So an amplifier is a signal strengthening kind of a device, right? All right. Now, so far I've talked about A being infinity, right? But in practice, even relatively modest amplification factors are good enough, right? So for example, if A is 100, right, then A over 1, over 1 plus A is 100 divided by 101, which is like 0.99, right? It's pretty decent already. So A doesn't have to be humongous in order to be high enough. So even something like 100 or a few hundred or 100,000 or 1,000, all these values are pretty reasonable and pretty usable for our purposes, right? So now if an op amp is in voltage comparator mode, one we just talked about, then I just want us to remember that this theorem doesn't apply. Okay, in other words, this theorem, okay, is only true, okay, when negative feedback is there, right? So only true when there's negative feedback. Otherwise, there's no reason for Vp and Vn, or the two inputs, to be identical. Now, you might be curious as to know what happens if I have positive feedback instead of negative feedback. In other words, what happens if I were to take the output and sort of stick it to this end, okay, instead of the other end, right? Now, suppose that this output voltage tries to increase a little bit, right? Let's say it tries to become V output plus delta V, right? Then what will happen is that this Vp is also going to go up. And that's going to get amplified by a huge number A, and it's going to get driven even higher. Okay? Now, and that's going to make it go even higher and so on. So this loop, okay, is basically an unstable situation creator, right? So a positive feedback loop results in accentuating any potential perturbations that might happen to the output, and it'll drive it to one extreme or the other, right? This is like an extremist, okay, crazy man, right? So now what's going to happen is that the output is going to get stuck at one of the two output extremes, plus VDC, okay, or minus VDC, okay? So to summarize again, okay, our first action step, okay, so let me call this step 1, okay, is to make sure that there is negative feedback, right? So let's talk a little bit more about this negative feedback, right? So what I'm saying is that there has to be a path for current to flow from the output to, okay, the negative terminal of the input, right? Now this feedback, okay, should work, okay, in DC as well. In other words, even with, without any frequency, at frequency equal to 0, right, this feedback path must still work for this op-amp to be happy and stable, right? So that means there must be either a resistor, or perhaps an inductor, or just a wire, which means a resistance equal to 0, connecting the output to the input, right? So we need the feedback to be, like a DC kind of feedback, right? Now, whenever this is true, okay, we simply know that these two voltages are going to be the same. And we simply exploit that fact in order to solve our circuits. Now, of course, the only other thing that we take advantage of is the fact that the input currents going into the op-amp are 0, right? So whenever we try to write down our Kirchhoff's current formulas, right, we know that this current is going to be 0 and this current is going to be 0. Okay, and that's mostly all there is to it. So what we'll do is let's just work through a series of examples to sort of get the hang of it. Okay, so let's revisit our voltage follower, right? So you got the op-amp, okay, and you got the input voltage, V input, and you got, a wire going from here to here. Okay, this is our V output. Okay, and this is just a straight wire going like that, right? So we can immediately write down the voltage at this point. The voltage at this point is simply going to be equal to V output, right? And we know that this voltage is going to be the same as this one, right? And this is V input. So we know immediately that V output equal to V input, right? That's all there is to it, right? So that's why it's easy to see that this circuit performs as a voltage follower, because the output voltage has to be equal to the input voltage, right? Because first of all, we have negative feedback, check, okay? And then as soon as we have that, we know that these two voltages have to be the same, and these two voltages have to be the same as that. So we got V output equals V input. Okay, so this is our good old voltage follower. Now we can work through more circuits. Okay, so let's try this circuit here. Okay, so you got an op amp. Okay, now suppose I were to take the plus thing and set it to 0. Okay, and the minus input, okay, is connected to the output like that. So I got a resistor. So this is my V output, and I got a resistor going into V input like that, right? Now it's more common to sketch the circuit the way you see on the screen, okay? But it's really the same thing. I just wanted to keep these pluses and minuses the same way for now, okay? But as long as you know what to look for, we'll be just fine. So now, first step, we make sure that we have negative feedback, right? So negative feedback, check, right? We got that. So now that we have negative feedback, we know that this voltage is going to be the same as this voltage. Now we know that this guy is at 0 because we connected him to ground, right? So that means this voltage will also be 0. So if this resistance is R1 and if this resistance is R2, then we can just solve this circuit. Now in solving the circuit, we also need to keep in mind that this current is 0, right? So that's all there is to it. So we know that this current going into this is going to be Vn minus 0 divided by R1. So it's going to be Vn divided by R1. So that's the current going in this way. Okay. So there is no current going this way. That means that all of this current is going to flow out like this, right? And this current is 0 minus V0 divided by R2. And these two currents are the same, right? So Vn over R1 equals minus VO output divided by R2, which means the V output is minus R2 over R1 times V input. Okay, so let's observe a few interesting things about this circuit, right? So this circuit takes an input voltage, Vin, and amplifies it by this factor. So this is sort of like the amplification, right? The overall amplification provided by this circuit, and it happens to be negative, right? So we call it an inverting amplification. So, okay, so the negative sign, okay, means that it's an inverting amplifier. Now what's also interesting is that this amplification only depends on the ratio of these two resistors, right? So if this ratio is 2 to 1, then the amplifier will be minus 2 times, okay, the output voltage will be minus 2 times the input voltage. It doesn't depend on the gain of the op amp itself. So if the op amp has a high enough gain, in other words, it's reasonably ideal, then you will get a very reliable amplification. So this number depends only on the accuracy with which you can get these two resistors. So if these two resistors are chosen precisely, okay, you can get a precise level of amplification. So for that reason, I will call it precise amplification. Okay. Now let's look at this other circuit here. So if we were to take the same op amp, okay, plus, minus. Now instead of applying 0 to this, suppose I apply an input voltage. here, okay? And I have the same kind of a feedback arrangement. So I have but in this case, what I do is that I set this guy, okay, to ground. That means this voltage is 0. Okay. Now we know that this voltage is the input. So that means that this voltage is also equal to the V input. Okay. And this voltage equal to the V output. And now we know that there is no current going in through this, zero current. That means all of the current that flows here will also have to flow here, right? So I can write down the current flowing this way as 0 minus V in divided by R1, which is minus V in divided by R1. And the current flowing here is V in minus V out divided by R2, right? So this should be equal to V in minus V output divided by R2. Okay? Okay, there you go. Didn't want to sketch it all over again. So anyway, so what that implies is that V output, okay, we can just work our way through this algebra, right? So V in, okay, I'll take this to the other side. I get 1 over R2 plus 1 over R1, okay? And I'll take this is VO divided by R2. So VO, okay, or V output is R1 plus R2 divided by R1, R2 times R2, okay, Vn. And this R2 cancels out, so we get R1 plus R2 divided by R1 times Vn. Okay, now we don't have a negative sign here, okay, so for that reason we call it a non-inverting, okay, amplifier. Okay, so we just derived the non-inverting amplifier. Let's go on to the next example. Okay, so the next example is a bit of a combination of the earlier two examples, okay, and we call it the differential or the difference amplifier. So the idea is to try and see if we can do, we can build a precise difference amplifier. Okay, remember the op-amp is a difference amplifier, but it's not precise because the amplification factor, okay, is not tightly controllable. Okay, so with the difference amplifier, okay, got a circuit that looks like this. This time let me just draw the minus on top and the plus at the bottom, okay, just because the way the circuit is drawn on your screen. Okay, this is R4, this is R3, okay, this input is V2, this input is V1, this is R1, this is R2, and this is V output. Okay. Now, the first thing we do, as always, is to make sure there is DC negative feedback, and we sort of see that happening here, right? So the negative feedback is good, nice and strong. It's kind of like Star Wars, you know, may the force be with you. This is a case of may the negative feedback be with you. So the force is strong here, the negative feedback is good. So what that means is that the voltage here and the voltage here are going to be essentially identical. Okay, suppose the voltage here is V, then the voltage here is also V. Okay, and now we can solve. Okay, there's no current going in like this. Okay, and there's no current going in like there. So everything else is pretty straightforward. Okay, now we can solve for the current that's going in here like that. It's V2 minus V divided by R3, and all of that current goes in like that, which is V minus 0 divided by R4, right? From that we can solve for V, right? So on the right hand side you got V times 1 over R4, okay? And then if I can move this term onto this side, it's 1 over R3 equals, okay? On the left hand side I got V2 over R3, okay? So V is 1 over R3 times R3 R4 divided by R3 plus R4 times V2. Look at that. Okay, this is kind of interesting. This is no different from a voltage divider. So if you have a voltage divider, right, V2, and you got a resistance R3, and you got the resistance, okay, R4, then the voltage at this point is R4 divided by R3 plus R4 times V2, and that's equal to V. Okay, so this is good. So we can use this voltage divider type of idea in solving these circuits. Okay, now let's work through the upper part, right? So V1 minus V divided by R1 is the current going in like that. Okay, now all of that current is going to go into this branch here, which is V minus V output divided by R2. Okay, so let's solve for this. So V1 over R1 minus V, which is R4 divided by R3 plus R4, okay, times V2, okay, divided by R1 equals V over R2, so which is R4 divided by R3 plus R4, okay, times V2, and this is divided by R2, okay, minus V0 over R2. So not V0, V output over R2 is R4 by R3 plus R4 R2 V2 plus R4 V2 R3 plus R4 R1, okay, minus V1 over R1. I can multiply throughout by R2, okay, and I get V output equals R4 by R3 plus R4 times V2 plus, okay, R4 R2 divided by R3 plus R2 times R1 minus R2 over R1 times V1. Okay? So if I were to simplify this, okay, let me see if I can do that. Okay, so V output is essentially, here you go, I can bring the common denominator, R3 plus R4, okay. I got R4, R1 plus, okay, I can have the denominator R1, then I have R4, R2, okay, this whole thing times V2, oh sorry, I had a V2 here, minus R2 over R1 times V1, okay. So this is equal to R1 plus R2 divided by R3 plus R4 times, okay, R4 divided by R1 V2 minus R2 over R1 V1. Now this expression looks a little messy, okay, and if you want to design a difference amplifier, what we want to try and do is we want to make this term, okay, essentially the same as this term. So we just get V2 minus V1 out of that, right? So one way to do that, okay, is to say R1 equals R3, okay, if R1 and R3 are the same, and if R2 equals R4, right, then this whole ratio goes away, right? So if R1 equals R3, okay, and R2 equals R4, okay, then we get, okay, this whole ratio is 1, and R4, if I replace it with R2, I get R2 over R1 V2 minus R2 over R1 V1, which is R2 over R1 times V2 minus V1. Okay, so this is a nice, beautiful difference amplifier. All right, I hope you're getting the hang of this. Okay, so let's work through another example. Okay, now this example is the summing amplifier, right? So it's the same as what we had before. Okay, so you got the op-amp circuit here. So you got negative feedback, nice and strong, with resistance R4. Okay, this is V output. Now at the input side of this, instead of just having one resistor, we got a bunch of them. So we got V1, we got V2, and each of them is connected to resistors R1 and R2, and we got voltage V3 connected to resistance R3, right? And the plus side is essentially connected to ground. Now on the circuit on your screen, you'll see that there's a resistance R5, right? Now this resistance R5 is only needed for a non-ideal op-amp, right? Because if it's connected to ground, it's connected to ground. The voltage is 0, right? There's no current flowing through this. Now the R5 was put in this circuit just to take care of, you know, the situation if the op-amp is non-ideal, which means there is some current flowing through that. So for our purposes, this current flowing through that and this current flowing through that is 0, so we'll actually ignore this resistor, you know, for our purposes, right? So if this voltage is 0, because it's connected to ground, then this voltage is also equal to 0, right? So we can basically see that there's a bunch of 3 currents converging onto this. The first of these currents is V1 over R1, flowing like that. Second current is V2 over R2, okay, flowing like that. And the third current is V3 over R3, flowing like that. And the sum of these three currents all flow into this resistor here, right? Because there is no current flowing into the op-amp, right? So the current flowing into that resistor is 0 minus V0 divided by R4, which means that, I keep calling it V0, it should be V out, okay? Let me call it V out equals, okay, minus R4 times V1 over R1 plus V2 over R2 plus V3 over R3. So this is a nice way to calculate the sum of a bunch of currents, right? If I wanted to calculate a weighted sum, I can choose these resistors appropriately, right? But it's an inverting sum, right? So it's an inverting or more precisely a summing amplifier, or an adder, basically an inverting adder. Okay, you can get amplification. So if you choose R4 greater than R1 or R2 or R3, you can amplify each of these signals even as you're adding them, right? You can also choose to attenuate them. So if R4 is less than R1, this V1 is going to get attenuated. So you can basically, pick these resistors R1, R2, R3, and R4 to get any weighted sum of V1, V2, and V3 that you like. Okay, it's a beautiful circuit, very useful. So now let's move beyond resistor circuits, okay, and start to look at circuits that involve other components, okay. And we saw in the previous lectures that given a circuit, it can be transformed into its S-domain version. So if I have a resistor R in a circuit, okay, this guy will stay the same. It doesn't look any different, right, in the Laplace domain. Now, if I have a capacitor C, okay, then this capacitor will become, in the Laplace domain, okay, 1 over SC, okay. Now, if I have an inductor, okay, L in the time domain, okay, so what's on the left is like the time domain picture. And what's on the right hand side is the S domain or the frequency domain picture, okay? So this inductor, we still sketch it the same way, except its impedance is going to be SL, okay? We call this Z sub R. We use the letter Z to indicate an impedance, and we use the letter Z again to indicate an impedance, but for a capacitor, so we write it Z sub C. And for an inductor, we write Z sub L. Okay? So by simply transforming a circuit to the S domain, we can start to think in terms of impedances. Okay? And an impedance is a more generalized notion that specializes to a resistance or a capacitance or an inductor or inductance or any combination of these, right? So, in the time domain, we're dealing with real numbers, okay? Whereas in the S domain, okay, we're dealing with complex versions. But there is a big benefit to using these because it'll simplify our analysis substantially. So let's work through an example. So this circuit is one that we used in our most recent test. Okay, so I got a V input. Okay, so this input is given in the time domain, right? So let me sketch it more neatly. Vi of t, right? So you got a resistor, you got a capacitor, like that, going to ground. Okay, and this goes to the plus input of the op-amp. Okay, And on the minus input of the op amp, I got a circuit that looks like this. Okay, this is VO of T. Okay, this is RF, and this is R1. Okay, so my first order of business is to essentially transform everything to the Laplace domain. Okay, now in the Laplace domain, this guy will still remain R. Okay, this guy will become 1 over SC. Okay, and this guy will remain R1, and this guy will remain R. Okay, and I'm all set to go. Now, again, rule number 1, is there negative feedback? So we sort of see that there is a beautiful resistive path going from the output to the input. Okay, so check, we got negative feedback. Now that we have negative feedback, we know that the voltage here, suppose we call it V, is the same as the voltage here, and we call it V. Okay, so in the Laplace domain, I'm going to call this Vi of S, and I'm going to call this Vo of S. Okay, and this voltage is going to be V of S, right? So now V of S, okay, is essentially the output of a voltage divider, right? Because there's no current going into this. That current is 0, and that current is 0, okay? So this is just a voltage divider, okay? So the VO of S is 1 over SC divided by R, sorry, this is just R, not R1, plus 1 over SC, okay, times VI of S. Now, there is also a voltage divider happening on this side, right? There's no current going in through this, so all the current that comes like that will flow like this, right? So this is actually just a voltage divider. So V of S can be written on this side, okay, as R1 divided by R1 plus RF, okay, times V output of S. Now we know that this and this are the same, okay? So we can just equate these two guys and we can solve for the output. That's all there is to it, right? So R1 divided by R1 plus RF times VO of S equals, okay, I'll multiply this top and bottom by SC, okay, so I get 1 over, okay, SCR plus 1 times VI of S. So this implies that VO of S, okay, equals R1 plus RF. Okay, I'm going to take this to the side. Okay, I'm going to take this to the new denominator. R1 times SCR plus 1 times V input of S. Voila, that's all there is to it. Okay, so let's go on to the next example. Now, in the next example, all we did was we swapped these two devices. Okay, the rest of it was pretty much the same. So let me sketch it. So we got V input. I'm going to just go to the Laplace domain right away. I'm just going to call it VI of S, okay? And there's a capacitor. So this is 1 over SC, okay? And there's a resistor, R, okay, going to ground. And this is going to the plus input of the op amp, okay? And on the minus input, I got the same voltage divider. So this is V output of S, okay? I'll call this R1, this is RF, okay? So if this voltage is V, then this is the same as this voltage V, okay? So I'm just going to equate this guy to this guy, okay? Because they're the same. So what that says, and again, this is a voltage divider. Okay, so voltage V equals, okay, R, V equals R divided by, okay, 1 over SC plus R times V input, and this is the same as the output coming from this voltage divider, which is R1 divided by R1 plus RF times V output of S. Okay, I can write out V output now. Now I'm just going to multiply the top and bottom by SC. Okay, so I get SCR divided by 1 plus SCR, okay, times V input, and now for the numerator, okay, I'm going to just move this whole guy to the other side, so it's R1 plus RF divided by R1 times V input of S, and that's our answer. Okay, it's fairly straightforward. So this circuit has a 0 that the other one didn't have, in addition to the pole, and the pole is in the same place for the two circuits. So with this in mind, we can basically, revisit our inverting amplifier. Remember this guy? Minus. So this one was set to ground. We used to have a resistor here. Now we can have a general impedance here. Okay. Suppose I call it Z sub F. And now we have a general impedance here. I'm going to draw a box to indicate that. Okay. And this is input VI. Okay. So this we call this ZI. Okay, so it looks like the same circuit, except before we used to have a resistor here and a resistor here. Now we can have some arbitrary impedances. Now, this circuit gets analyzed much the way as any of the resistor-based circuits, except we do everything in the complex domain, right? That's the only thing. So we have VI of S, okay, on this side. ZI is a complex impedance, ZF is a complex impedance, and the rest is more or less the same. So we know the voltage here, which is 0, because this guy is connected to ground. And, we have negative feedback here. Okay, I'll say a bit more about that. So for example, for now, we'll assume that there is negative feedback, right? That this impedance has some resistive, component to it, so that there is some negative feedback, right? So suppose we assume negative feedback. Okay, I cannot take this for granted, okay? Because what if there is a capacitor here? Then there won't be a DC path from here to here, okay? So we'll assume that this impedance is such that there is negative feedback. Under this assumption, we know that the voltage here is going to be 0, okay? And the currents going into the op-amp are 0, okay? So this current is going to be equal to this current. So VI of S divided by ZI, okay, equals 0 minus V0, okay, which is minus V0 of S divided by ZF, which means the output voltage equals, okay, minus ZF by ZI times the input voltage. Again, this whole thing is in the Laplace domain. Okay, so now we can specialize this circuit to any of the special cases that we looked at before. So for example, suppose I set ZF equal to RF and ZI equal to RI, then I get a purely resistive circuit. Okay, this was my inverting amplifier. Okay, the good old situation. Now, if I set reuse the same sheet of paper. Now, suppose I say for the same circuit, okay, that ZF is still a resistor, but suppose for ZI, I set it to be a capacitor. So the impedance is 1 over SC, okay? Then the output, VO of S, is still the same, okay? Still the ratio of minus ZF by ZI times VI of S, which is, okay, R minus, with a minus sign, okay, divided by ZI. So we actually multiply it by SC, dividing by 1 over SC, okay? So this is SC VI of S minus SCR VI of S, okay? Now, in the Laplace domain, multiplying by S means that you're differentiating the input signal, right? So this is a differentiator. Okay, let me sketch it out. So this is actually quite intuitive, right? So now let's go through the analysis again. This voltage is 0, so this voltage is 0. That means the current going through this is the current that goes through the capacitor, all right? So if this capacitor is C, right, then the voltage across that is just VI, because it's VI minus 0, right? So the current that goes through this, okay, is C times dV by dt, right? C dVi by dt. Now all of this current is going to build up a voltage across this, right? So the output voltage, okay, is given by, okay, so if we want to solve for this, it's VO. Let's look for this current, okay? So we know that this current I flows here, okay, all of it, because the current going into the op amp is 0, right? So this current is given by, okay, so this current I can be written as 0 minus V0, which is minus V0, divided by this resistance R, right? So we can rewrite the same thing as V0, okay, equals minus RC dVi by dt. Okay, so all of this makes sense. So this is a beautiful differentiator. Okay, so it checks out both ways. Now let's swap the resistor and the capacitor and see what happens. Okay, so suppose now that I set ZF equals a capacitor, so it's 1 over SC, and ZI is a resistor, so it's just R, then VO of S equals minus, okay, ZF, which is 1 over SC, okay, divided by ZI, okay, which is 1 over R times V input S. So this is minus 1 over SCR VI of S. Okay, so we know from our knowledge of Laplace transform that this is basically an integrator, an integration, right? Actually, you can think of this as an inverting integrator. Right? Because there's a minus sign there. Okay. Now, let's take a closer look at this circuit. Let's sketch it out. okay? So if you sketch it out, it kind of looks like this. You got your input voltage here, you got the resistor R, okay, and you got the capacitor C, okay, and this is connecting to the input, negative input, and this has got the positive input like that, okay, like that, and this is your output, okay. Now we sort of notice that there is a break here, okay. So for this particular case, okay, there is, we don't have negative input, okay. So we have a situation here, right? But on the other hand, an integrator is a nice thing to have, right? So what do we do in practice, right? What we do in practice is we try to approximate this guy, right? So let's see how we do that. So we saw that we had the integrator circuit, which has an R, a C, okay, like that. This is sort of the ideal integrator, but because we lack a feedback path, okay, what we can do in this case is that we can stick a resistor here, okay, and this resistor, okay, let me call it R sub F, is a resistor that's just intended to give a little bit of negative feedback. Now remember, if the op-amp's gain is very high, this resistor doesn't have to be all that big. Just the tiniest of, leakage current is going to stabilize this op-amp, okay? So in this case, okay, we can go back to our good old circuit, and we have ZF is simply RF parallel the impedance of the capacitor, which is 1 over SC, okay, and our ZI is R, okay, and our output is minus, okay, ZF, which is RF parallel 1 over SC divided by R, oh, let me call this RI, okay, RI times VI of S, okay. So by choosing this value of R, suitably, we can make this integrator, as close as possible to the ideal integrator and have it yet be stable, okay? Another way to think about it is that by choosing these values of resistors and capacitors, we can place the pole where we want it, okay? That's another way to think about it. But in the end, it's really about that negative feedback, right? For the DC case. So even a slight leakage resistor, something very high, like thousands of ohms, or millions of ohms or something, or tens of millions of ohms will make the circuit work. We talked about the inverting adder, okay? I think we already did that before. I don't know why I have this slide repeating here. Now adders are pretty interesting because they're used in our music systems, right? So if you have multiple sources of sound, maybe a guitar, a sort of drums, and a voice, and something else, some wind instrument or something like that. Each of these will have a microphone of their own, right? And by using a thing like this, okay, it's called a mixer actually, you can actually add all these sounds together, and by adjusting these dials that you see on the lower left, right, you can, balance the different sounds, perfectly. Now, one of the things about, real-world systems is that they can be composed of multiple systems, because if you're going to build something very complicated, it's very difficult to imagine the whole thing right from scratch, okay? It's much more practical to think of it in terms of a series of building blocks, right? So for example, if H1 of S, okay, is one system that you built, maybe it's a differentiator, right? And then you can connect the output of that to some other system, say H2 of S. Maybe it's an adder, right? And so if X of S is the input and Y of S is the output, now in the Laplace domain, when you cascade systems like that, okay, the Laplace transforms get multiplied, right? If it was in the time domain, then we would have to convolve these two guys, right? So basically Y of S in this case, okay, is simply H1 of S times H2 of S, okay, times X of S, right? And this whole thing can be thought of as one complicated system that can be broken down into two simpler systems like this. Now, sometimes what happens, now that we know how to add, okay, we can also add things. So suppose I have X of S, okay, a signal. I can give it as an input to two different subsystems, okay. Say I have H1 of S, and suppose I have something else that's H2 of S, okay. Then what I can do is that I can bring these two guys and add them together, okay, and the output is Y of S. Now, these ideas can be brought together to build something, quite a bit more sophisticated and interesting. Okay, let's see how to do that. So we had talked about the idea of a negative feedback before, right? So now it turns out that this simple idea that we talked about in the case of an op-amp is a much broader and more powerful idea that can be used to build, complex systems. Now, one of these particular systems is called a control system, okay? So the idea is that suppose you have an input X of S, okay? You essentially feed it into a differential amplifier, okay? So this one goes in with a plus sign, okay? The other input actually comes in with a minus sign, okay? And this is essentially an adder, okay? Now, this difference is what we call the error, E of S, okay? And it's fed to H1 of S, it's one system, okay? And the output of H1 of S is processed by another system, H2 of S, okay? And that's the signal that's fed back here, okay? So we have negative feedback, right? So that means this system will hopefully be stable, okay? The output is Y of S. Now, we're talking about much more than the little op-amp here, right? We're talking about, very complex systems, H1 and H2, that by themselves could be built of other complex systems, either in cascade or in parallel, whatever, right? But all these things are coming together to form, okay, this type of a circuit, right? And let's calculate sort of, what the behavior of the circuit is going to be like. So the error signal, E of S, is the difference between X of S, okay, this guy, and, minus H2 of S. But this H2 of S, okay, is processing Y of S, right? So whatever the signal Y of S is being processed by H2. So that's what this product is. And the beauty of Laplace transforms is that this becomes a simple product, right? If we were to do it in the time domain, then we're taking this signal Y of S and we have to convolve it with this system, right? And then feed it into this differencing circuit, okay? Now, also we can write Y of S, okay, is simply E of S, which is the error signal going in, being processed by H1 of S, right? So it is H1 of S, E of S. Right? So we can essentially, substitute for E of S here, okay? So Y of S equals H1 of S times we will substitute for E of s here, right? Which is x of s minus h2 of s, y of s. Now y of s appears, on the left-hand side and on the right-hand side. So we can basically rearrange this equation a little bit. So we can say y of s times 1 plus, I'll take this whole thing on the other side. You get h2 of s, okay, times h1 of s, okay, times y of s, which is over here, equals, okay, h1 of s times x of s, which implies y of s by x of s. This is our transfer function. Okay, this is the overall transfer function for this circuit is h1 of s divided by 1 plus h2 of s, h1 of s, like that. So this is kind of interesting, okay, because you got a remarkably complex system that turned out to be relatively easy to analyze, okay, and this is possible because of the beauty of Laplace transforms. It makes it so easy for us. If we had to do it in a time domain or try to even imagine how this a circuit works, we'll have to go through a lot more detailed thinking than we just did. Okay. Now, this is the subject of an entire course. Okay, so you're going to take a course on control systems where these kinds of systems will be explored in much greater detail. Okay, so for the purpose of this course, we're going to kind of leave it at this level, except what we'll do is that we'll just take a quick look at an example, right? Okay, so we're given this very complicated looking circuit. It's got three different op amps, op amp 1, op amp 2, and op amp 3, and we have to figure out how to deal with this, right? So one of the strategies that we want to employ is to start to recognize some of the standard patterns, right? So what you see on the upper left is basically an inverting amplifier, right? But this one has the addition capability, so it's got two different inputs. Okay, so one input is x of s, okay, and the other input is like the feedback input that's coming in from op amp number 3, okay, and then what this guy does is that he basically does an inverting summation of these two guys, right? So what comes out at this end is the signal E of s, okay, and E of s equals, okay, now the ratio of the feedback resistor to the input resistor is just 1 in this case, so it's just minus, okay, x of s plus, okay, this thing. Suppose for now let me call this z of s, okay, z of s. So this is what's going on with the op amp on the upper left. Okay, so this is just an inverting summer, okay, or an inverting adder. Okay, basically. Now the op amp, so this is op amp number 1. Okay. Now for op amp number 2, what's going on is that we have the signal E of s going in, okay, and this signal is getting integrated, right? Okay, and what's coming out of this, okay, is, but this is an inverting integrator, okay, so it's minus 1 over SCR, okay, times E of s, and this equal to Y of s, okay. Now RC in our case is basically 0.5 second, okay. So basically this signal, this system is like minus 2 over S times E of S. So this is Y of S. Okay, now if we look at op amp number 3, okay, it's just your standard inverting amplifier. Okay, so what comes out of it is Z of S. Okay, and Z of S is minus 0.2 R divided by R, which cancels, times Y of S. Okay, so if you plug in these three things, okay, we get the situation that looks like this, right? So we can just simply solve this circuit. Okay, so E of S is minus X of S, okay, minus, okay, minus 0.2 Y of S. So this is the same as minus X of S plus 0.2 Y of S. Okay. Now Y of S is H1, which is minus 2 over S, okay, E of S, right? And E of S, I know that from this formula, is minus X of S plus 0.2 Y of S. So at this point, we can simply solve for X of S. So I got Y of S on the left-hand side. 1, I'm going to take this guy to the left-hand side, plus 2 times 0.2 over S equals, okay, this negative sign and this negative sign will cancel, so I get 2 over S X of S on the right hand side. Can multiply throughout by S, and I can solve for Y. Okay, so Y of S equals 2 over S plus 0.4, okay, 2 times 0.2 is 0.4 times X of S. Okay, so this very complicated system turns out to have a very nice and clean looking transfer function in the end. Okay, and that's the power of Laplace transforms again. What we have done to solve this example is to use several of the things we talked about earlier, right? We've sort of talked about a bunch of basic op-amp circuits, and if we become familiar with these, we can start to recognize patterns, right? And once we recognize these patterns, we know what these circuits do, right? And since the output of an op-amp can put out any amount of current, right, we can treat each of these op-amps as 3 different individual entities, right? And then we can use the properties of the Laplace transform to essentially combine these systems, okay, into more complex systems. And we looked at several different standard, patterns, right? One of them was the 2 systems in series. The other one was 2 systems in parallel. And then we looked at the feedback control system, right? We've used all of these ideas in combination to work this example. So what we've done is we've been able to understand the behavior of a relatively complex op-amp circuit that was given to us, okay, and sort of figure out in a relatively simple way what it does. Okay, so what we've done today is to learn how to analyze op-amp circuits. And the best way to do that is to work entirely in the Laplace domain, okay, or the S domain. Now, we talked about the basic steps to analyzing a circuit with op-amps. First and foremost, make sure that the circuit is in stable form, right? So speaking of which, coming back to our example here, okay, the op-amp number 2 was not in stable form, but what we can do in practice is to assume that there is a resistor in parallel with the capacitor C. Okay, and that resistor's value is so high that it's almost like non-existent. okay? But it provides the negative feedback, and for all practical purposes, we can think of this circuit as a pure integrator, right? So the analysis that we did is in that sense approximate, okay? So all op amps must have negative DC feedback, okay? And then whenever that is true, the two input voltages to an op amp are equal, right? So if you have an op amp, right, you got the positive voltage, the negative voltage, and the output voltage. Basically, when it's in feedback, these two guys are the same, okay? And then these two currents are zero. So as long as we just embed these constraints into the circuit, okay, the circuit analysis is, as you know, very straightforward, right? You just need to know that this voltage is VO, this voltage is the same as this voltage, and there's no current going in there, right? You can use whatever circuit analysis technique you're most comfortable with, you know, KCL, the KVL, the voltage divider, and any other tricks that you'll learn along the way. They're all fair game, and you can apply them. We also learned how to build complex systems by connecting simpler systems in a variety of ways, and we learned specifically 3 different ways. One of them is the cascade, okay? The other one is, you know, systems in parallel and systems in feedback. So we can start to put all these kinds of knowledge together to analyze, okay, remarkably complex systems. Thank you, and I hope you found this video lecture to be helpful.